I was looking at the reports on the lab for the course project, and so Noah was not here last time. I don't know, I forgot if Van was here. So the video, definitely watch the video after this class, so you know what are the tasks you have to do. There's a, SAR logic block is due today, and watch the videos and you can find it out. I don't know if you clicked the link yesterday. We have the SAR done already, okay. Yeah, the link was dead. I just found it 2 hours ago. I don't know. I upload the video. Because every time when someone is not here, I will try to upload the video as soon as possible so they are not missing any assignments.
One thing, the model file.
Yeah. But you have been using that for the labs, right?
Well, no, we use the C5 models text.
Yeah. Doesn't work?
It doesn't work with all my old logic gates. And I don't have the models text. So all the logic gates I used to build this are.
Oh, because you have to change the name of it. If you download the old project, the design files.
Yeah, but like the way you're labeling transistors with the models text is different.
That's right. So you have to change the model name. Right. So it's just NMOS and PMOS. But you have been doing that in the labs, right?
Yeah.
That's the same C5 model.
Labeling LT spice.
But you are doing it in lec36 for the course project, for the SAR. Not LT spice. See? No. So let's see. See? That must be done in lec36 instead of LT spice. Maybe I should, maybe I should make this more clear. The first version, I think I stated super clear. I said this must be done in lec36, but here I just said duplicate. No, I never say that. Did I say that? No. The last homework. That's right. Yeah. But for this one, remember I was saying we should finish the layout in lec36, but I eventually found this not realistic, so I removed that task, remember? So it's just a simulation, but in lec36, which is one step away from getting the layout done. It's actually, if you get everything done in lec36, if the simulation works, for example, we can recover that sine wave. We just don't have the tape out foundry. None of the foundries are doing C5 fabrication anymore. But it used to be free, right? That was in 2018, I think. I did it in my analog class. Every single student get a chip. It was 5 chips in the package and 20 dies on the little box, and that was so 5 packages and 20 dies for each student. I think I had like 20 something students in the lab in that class. So eventually I received a lot of chips with the packages for free. Yeah, no, that was in analog. That was the OPAM design, which is not here, but I think it was a very similar OPAM to the one that you have here, right? Had the little capacitor on it. But I think if we can fabricate this one with C5 using lec36, just whatever you guys are doing now, okay, just convert it, going one step further to get the layout done. We send it out for fabrication, and if you receive the chip, if it works for simulation, it should work for your benchtop testing as well. You connect to the oscilloscope, you should be able to see recover sine wave. Okay, and there was a project done by, I think, Columbia University a few years ago. That was the main reference for this project, And they already removed the project and demonstration on their website. I don't know why, but so that was a year-long project in the 600 level ECE class, electrical computer engineering class in Columbia University. So the students are mainly either PhDs and master's students. So they actually fabricated using 130 nanometer technology with IBM. I think that was probably a grant for them from IBM. And what they did is they had ADC fabricated and plug into the PCB board and feed a music signal into the board, into the ADC, right? Just voltages, the music, just whatever electric voltages, and they digitize that signal using ADC, so it becomes 8-bit digital signal, 1 zeros, right? So 1 zeros are not able to drive a speaker. 1 zeros, it's gonna boom, boom. So it's just 8 bits, right? So you are not using digital signal to drive a speaker. The speaker needs to be driven by an analog signal. You know that, right? Okay. So the digitized signal as the output of the ADC, and then they put a R2R resistor DAC on the board. You can see it's an op-amp with a R2R on it. So the digital signal is being fed into that onboard DAC, and then there will be just one single output, which is the analog voltage, and that one is being amplified and then driving the speaker. So actually they were able to recover that music. So if you use your phone and cut a wire, for example, from the cable, right? And that's a super tiny analog voltage, like in millivolts. I don't know if you know that. It's just millivolts sound analog voltage, right? You plug in, put in the board onto the board and amplify that, preamplify that a little bit. So it's gonna be you bring it into the range of the ADC, okay? And then fit into the ADC and digitize it, and then DAC, and then connect to the speaker. Right. So this is just a way to verify it by your ear, so you can listen to the music. You know it's working, right? But to measure the details of the ADC, you just have to spend time on it. For example, when you do the simulation, you have to export the data and put in a sprite sheet, and to compare the ideal values, so you can get the DNL and NLs. And there are a couple other parameters you have to monitor, right? But the scope of this project is just a simulation in electrical SI. We just don't have enough time to do more, right? And do you have any questions regarding the SAR logic simulation? So you are good on that?
The other thing is the link on your website. Yeah, that was the main issue.
Yeah, because that was based on 50 nanometer technology. That was a 1 volt.
No, on your website.
Oh, you mean you couldn't even download it?
It doesn't work.
Which link?
Like, whatever.
These ones?
No, like on your main website.
Oh, okay.
Just the general spice model file.
Do you know where's that? Mm-hmm. Homepage of mine? Oh, here? Of the lab?
No.
Here? Oh, here. How did you find here? Good to know, though. Yeah. Yeah. Mm. Okay, good to know. All right. But you have used the C5 model file for your labs.
Yeah, I have those. Those were just not working with the old logic gates I had. Following the old tutorials for logic gates, I had to rebuild a bunch of them.
Oh. Okay.
I spent all week rebuilding logic gates from 241. Using those tutorials, which use the old model file. So none of the parameters you set in LB Spice work with the new C5 model file. Okay.
So if you,
if I'm supposed to be doing it in electric, it doesn't matter.
okay, but it's the same thing, right? So the model file are the same model files. It doesn't matter which software you're using.
They can't find the correct. Because normally you go in and you set the length with transistors, you can't find the parameters.
it must be a different problem though. It's not a model files problem. Mm-hmm. Because it's eventually our electric VLSI is not a simulation tool.
Well, I was trying to
I know. Yeah, I know. But eventually, this simulation is done by LT-SPICE, not electric VLSI. So when you are doing electric VLSI in the lab, it's also using LT-SPICE. So if that worked already, it should work for just pure electric VLSI, LT-SPICE simulation as well. So yeah, I've been using the same simulation tool by far.
yeah, I guess I just
Uh-huh.
don't know in Spice.
Okay. Okay.
For the C5.
Okay.
But not.
Okay. If you need help, you can
Yeah.
you can ask me. I think I will be there from 2 to 4 today. Okay. Mm-hmm. So after the the Thanksgiving break, there will be a couple of other lectures, and I will give you access to the server and give you a few other tasks on Cadence. Will be easier, but I think I'm not trying to just lecture for the rest 2 weeks for the semester. I can, but I think it's probably more helpful to let you guys follow the tutorials. We in that way, we probably still need the time to sit in the lab on Tuesdays, kind of 3-hour block, because this is a how many credits? Like 7? You're getting 7? No, 4 credits from this class, right? So, yep, we'll see. Okay, I'll get the plan listed on the website during the break and let you guys know.
Do you want the comparative done by break Friday, or do you want it maybe?
I don't want to give you some assignments during the break. So I think
Is this
it's 20. Hmm?
24? Isn't that
24 is, oh, sorry, I got to change it. Yeah.
Saying you didn't want break work, but then there was break work?
I know, but I'm trying to not put in break work, for you guys. Because that's in the US. In China, like people don't break at all. I'm in the US, I'm Americanized. Don't treat me as a Chinese. So I've never had any breaks in my like undergraduate, in my master's, my PhD, in my postdoc. Like weekends are not weekends at all. I never have any concept about taking breaks. I enjoy the breaks. I know this is wrong, but it's been like that for super long time until I was 30 years old. Got a job here teaching as a professor. I enjoyed all the breaks, take all the breaks off. Yeah. All right. I will change the date, so I'm sorry for that. Okay. So there will be a couple of things I need to talk about today. It's very important, so I don't want to miss it. For the rest of the semester, about 2 weeks, a little bit more than 2 weeks, we just have to cover the models and memory circuit. Introduction to the memory circuit. Then we're done. Okay. And for the cadence, we'll do a little bit layout with the cadence manual layout and also run some RTL to layout conversion, which is really fun, which is whatever the people in the industry do. Okay. But I don't want you guys directly jump into that kind of technique directly. If you want to work more on it, I will be able to get you a contract to work on that in the spring. Okay. Maybe you, or if you are interested in the spring, Jesse will be graduating. If you want to come back and work on this a little bit, you're welcome to do so. We had a history hiring Nick, who graduated and got into graduate school in CSU, but kept working with me for another like 3 months, and then he published a journal article on the Raman spectroscopy, which is awesome. So you'll be hired as a consultant instead of student. have to start with Miller effect. If you have a capacitor in the middle, the reason we model it this way is because it's exactly the same way that it works as a transistor or NMOS or PMOS. So if you have a voltage connect to one side of the capacitor, and on the other side, we are pulling it down to ground at the same time. So this is changing from 0 to VDD, and this is dropping from VDD to 0 at the same time. This is slightly different, right? Compared to like just driving one side, but now you are doing this kind of transition on both sides. It could be slightly difficult to understand, but let me tell you the conclusion here. So what's going on is, because this one is pumping charges to it and this one is pulling charges out, they're actually having two sources acting at the same time. So what's happening is the Q used to be, if you only have one source, you know, it's used to be delta Q, it's just a Q, all right? That's the amount of charges being changed across the capacitor. But now, because you are having two sources having opposite actions, behaviors here at the same time, so delta Q becomes 2Q. That's the starting point of the Miller effect. You have to understand why it's getting 2Q, because you have two sources. One is injecting, one is pulling. So the effective charges happening or changing the delta Q across the two plates is actually 2Q. And remember, Q equals V times C from circuit 1. That's a voltage change, that's a capacitance of the capacitor. How do you remember this equation? So that's a queen on the top, right? And there are two assists, one is Victor, one is Charlie. Okay. So it's Q over V equals C, Q over C equals V, Q equals V times C. All right. So in that case, you're having 2Q equals VD times C. And now the effective C becomes 2Q over VD. Because the capacitance is just a constant for the device, right? But whenever you have two sources, one is pumping, one is pulling, the effective C becomes 2C because of that. It's called Miller effect. So C effective C equals to 2C, which is the physical capacitance of the cap. All right. Okay, that's what's happening here. It's very difficult to visualize what's really happening, but you just need to know. It's a very simple concept actually. You have two sources. One is pumping, one is pushing, one is pulling. Okay, at the same time. Then the effective C here will be twice as much as the physical capacitance is for the capacitor. That's called Miller effect. Just remember that. Okay. So in that case, if you have a NMOS transistor, like this, and for the gate, you turn it down from 0 to VDD for digital circuits. And this one has a resistor and shorted to VDD on the top. And here's the output, that's ground. If you look at the cross-sectional view of it, so if you split it into two halves, if this is a capacitor here, it does have, if the overall physical capacitance is called COX, for example, COX, it's the capacitance of the oxide between the gate and substrate. So a half of it will be a half COX, and here will be another half COX. Right? That's how we model it. So in here, in the symbol, we model it this way. There are two parasitic capacitance. because of the gate and substrate capacitor. There's an oxide layer in the middle. So we model each capacitor to be a half of Cox. So Cox is COX is the capacitance of the gate, and that equals to the parameter, which is determined by the process. Determined fabrication process. Cannot change it because the gate has a certain distance from the substrate, right? If the C5, you have a constant distance over here and constant dielectric material here as well. So that's the parameter you can find from the process, and times W over L, which is the area of the gate and substrate overlap, which will be the COX, okay? So that's how to find the COX from the process. And we modeled it this way. So we divide it into two halves. If you know the width and length of it, right? If you know the width and length, you should know the COX because this is given, right? Okay. And because when you turn on, you will turn on this guy. This point, before you turn it on, this point stored a VDD over here, right? Before you turn it on, this one is being put up to VDD. It's 5 volts or VD, okay? If you turn this on, this point will be put down to ground. So perform the same as what we just modeled over here. One is turning on, and the other one is pulling it down to ground. Does that make sense? Okay. So which capacitor is going to have a mirror effect over here? So which capacitor is going to have a mirror effect? So it's driving this node, right? If you look at this circuit, so the voltage is driving this up to VDD, and at the same time on the other side of the cap, it's pulling it down to VDD. Okay, so two sources has one cap in the middle. So this one becomes 2C instead of 1C. So if you look at here, which is a similar capacitor compared to the model here? Which one? Which capacitor has lower on the upper one? So this one has been ground always, right? This node has been ground. It's not changing. It's shorted to ground. But this node was VDD, and now it's being put down to ground, right? So it's like this is going up, this is going down. So effective capacitance of this guy becomes what? Yeah. Are we missing another COX or not? So what's happening is, for when we have a mirror effect here, we look at the input and output separately. So for the input, it's being modeled like this. It's a 2C here. For the output, we modeled this way. And since we are looking at the input and output separately, we're not doing them together, so it's not basically 4C here. But when we analyze each one, each source is seeing a 2C over here. Okay, if this is C, and we model it this way, input seeing a 2C, but output also seeing a 2C over here. The reason we are separating them is because we are looking at the input capacitance and the output capacitance separately in order to calculate the time delay for input and output, right? So now, if we have a a half COX over here, it's going to give you one COX for the input and one COX out at the output as well. Like this. 2C for input, 2C for output. Okay? So it's 2C, it's going to be COX for input and also COX for output. So in that case, what is the total input capacitance for this NMOS? C in. What is C in here? Because these two capacitors are in parallel. All right. AC is different from DC. Okay, so AC is seeing these capacitors, not the other things. Okay, the AC can pass capacitors, and so it has to charge up these two capacitors at the same time, right? So we're having one COX here and a half COX here, so the effective C is actually 3/2 of COX. Right, and C out, the output capacitance is just one COX. All right, done. That's everything about the capacitor, parasitic capacitors of the NMOS. But it also has a channel resistance. You know, when we are looking at the time delay, it's 0.RC. So R also takes a role in the time delay because it's limiting currents. So we have to consider the channel resistance here as well. So eventually we modeled this NMOS transistor this way. This is the input capacitance. And here's the channel resistance. Let's call it Rn. It's a resistance to the N channel. So why we short it to ground? Why we model it this way? It looks so weird. Why we do it this way? Because when you turn it on, it runs through the channel. So this is like the channel. And all the capacitors are shorted to ground. It can be confusing. Why do we short the capacitors to ground? Because this one is modeled to short AC to ground. What about this one? Yeah, this can be confusing. When I was in graduate school, looking at all the models, why you always pull the point to ground? It's weird. Because when the channel is on, it's very similar that you are shorting this one to ground. There's the concept, you probably have never heard about it. I don't know if analog have taught you that. So DC is the AC ground. DC source is the AC ground. You have to be equivalent to this one, right? It's not like a purpose we're designing a circuit. Your model is this way, it has to be equivalent to this. That's why we model it this way. The DC source is just the ground. DC source. If you have just a DC signal, just DC source, that point will be a ground. For example, here, when you have something connect to the DC source, it's going to be a ground. I think when we model this one, we are not considering the pull-up resistor here. This is just a circuit where we analyze it. But eventually, if it's just so this model is exactly this, okay? It doesn't have a pull-up resistor here, all right? So this point is actually shorted to VDD. Mm-hmm. And the DC source, like here, the DC source is the AC ground. So when anything shorted to a DC source, you have to, when you do AC analysis, it becomes the AC ground. Why is that? Have you ever thought about it? I mean, when I was in school, nobody told me that. I mean, you look at the textbooks, all the analog 1, 2, 3, all the different levels, like 600, 700 level analog classes, when they do the modeling. Have you done AC analysis in analog?
Yeah.
You know, for AC analysis, you remove all the DC components, right? And you ground DC, right? Why we ground DC source in AC analysis? It's super confusing, but it's very simple. But you did AC analysis, but you didn't ground DC, DC,
So
or
we probably did.
but you didn't
Remember if
pay attention to it.
we're more focused on the AC analysis. You do this with a
Yeah,
I don't know why.
you don't know why, but you just did it, right?
Yeah. If you told us why, probably didn't know.
Yeah, yeah. It's a superposition in circuit analysis. DC is being added to AC. If you do it in oscilloscope, there's a DC and AC coupling. Remember that? If you connect the DC through the DC coupling, then everything will pass through. If you do AC coupling, DC will be removed. So DC and AC are being put together like a superposition or superimposed to each other, right? If you have a DC here, DC source, which means you have no AC at all, right? No AC. If you have, for example, like this, DC voltage. I'm just asking a question for a super circuit connection. 5 volts, 1 millivolt. Can you place two power sources? One is providing AC signal, one is providing a DC signal like this, and output it to somewhere or probe it in the oscilloscope? It's a very practical question. Okay, if you don't know that, and in your job you are connecting a circuit using two power sources or two sources in the lab. So you have a function generator here, right? Function generator has a little connector as an output. So that function generator will have a positive and negative. That's plus minus. So it's providing a voltage difference between these two terminals, which will be a sine wave or whatever. Okay. And usually we ground this guy. If you ground this guy, then whatever here will be the signal. Okay, it's a sine wave. Okay. And a lot of times this is connected to the ground of the cable through the power supply. So the power cable has, the cable, right, plug into the wall that has 3 terminals, and usually this is shorted to here, so you cannot actually put it in series. The reason is if you have a DC, for example, this is a DC power voltage, you got 2 connectors, plus minus, and actually they are separated. So this is not physically grounded to here. Okay, so in that case, are you able to put these two sources in series in order to have a sine wave being offset around 5 volts? And this is 1 millivolt swing. You know what I mean? Do you understand what I'm saying here? Yeah, learning from the textbook and doing some practical stuff is different. Okay, so what I'm saying here is, can you add a 5 volts offset to a 1 millivolt signal by doing a series connection between these two sources if you have this kind of two equipment in the lab? Yes, but for this guy, usually the cable for the function generator the ground cable is shorted to the building ground. Okay, so you can actually you cannot break it, right? You cannot break it here and insert a DC source in here. You know, for example, this guy is just a battery, right? Have a plus minus is a battery like this, right? It's a battery, okay? This one is not shorted to the building ground. It's a floating cathode. Okay, why I can tell that? That's the sound wave. Okay, that's the sound wave. I'm trying to add, so the sound wave is swinging around 0 volts. No, that ground cable is not floating. It's not a floating ground. It's a building ground. It's connected to this core here. So which means so if for example, have you seen the oscilloscope probe, right? So it has a cable, okay, and has a little wire here, right? Has a clip, right? Okay, and that one is a building ground, okay. You cannot break it and insert something in there. You know what I mean? But this is a floating cathode. It's just a voltage difference between these two. So what you can do is add this guy. So if you want to add a DC offset to this function generator, you can still do it. You cannot insert the battery here because you cannot break that line, right? But what you can do is you can add this one after this. You know what I mean? So connect this guy, connect this one here, all right, and ground this one to your circuit ground on the board, and use this one as the final output. So you have output, ground, but they are being put in series because plus, minus, which is the ground, you cannot break. But you cannot swap the location of it. You know what I mean?
So the way you drew it is the way we can.
Yes, this is the way you can do. You can make this happen. You can add a DC offset to it. But think about that. Can we have this one? Can we have this one as a final output? This terminal as a final output, and this terminal as a ground, which means the function generator, right? So we have a function generator here, right? This is not floating. Keep in mind, this is connected to the cable. Okay, all right. And then you add a floating DC voltage to the bottom, and you ground here. And you are thinking, hey, this output, if I probe it, it's going to show a nice DC offset for the 1 millivolt swing. Will this work, and why not working? Yeah, so this one is failed, right? It's not going to work. Okay, if you don't know this, you're stuck there forever. And for the if we just probe, okay, so let's come back to the topic. If we are connecting the circuits like this, all right, so this is the wrong way to do it. Okay, so the correct way to do it is we have a DC power supply and then the function generator. Okay, this is okay. And if we only look at the AC voltage on the oscilloscope, we're having a AC coupling. This one will be gone. This one will be gone. Why? So this is another concept. What's the input resistance or internal resistance of a DC power supply? You need to know that. What is the ideal input resistance of DC power supply? Like this one. If we are doing AC analysis, we only look at this AC signal. We are treating this guy as what? As a wire, because the input resistance of DC power supply is 0 ohms. You need to know that in your mind, okay? You're dealing with electrical stuff. So this is 0. Right? So when you are dealing with AC analysis, a DC source will be what? Will be a wire to ground. Why? So look at this guy, the VDD here. Yeah, so let's come back to this one. So the DC power source will be a wire in here. It's a wire, just a wire. Why is it ground? Why it is ground? Why for AC analysis it's AC ground? That's right. Yeah, exactly. Yeah. Let's see this one. If I drew a VDD here, what does that mean? It's a power supply. Okay, if you draw the physical connection of the power supply, this is how that works, right? This is what you do in the circuit. Okay, so if you have a capacitor here, which is you're trying to model this capacitor in the circuit. So DC source will be AC what? DC source is AC ground. Does that make sense? Okay, so we model this guy. Can I just model it like this? It's like you grab this pin and rotate it and put the ground. Make sense? Okay. So we can do this definitely. It's legit. Okay. So tell me what's the capacitance of this guy if we model the NMOS simply, a very simple NMOS like this. Okay. This is a VDD, right? This is ground. That's how we model it. So this simple transistor is being modeled this way. So the whole thing here is a transistor. So this ground is this ground. But you have to have this in order to model it this way for the mirror effect, right? So now tell me what's the capacitance of this guy? That's the input, that's C in, right? What is C in? And why do I draw it this way? Why do I draw it this way? Why have to isolate it? Why there's no wire here? Do you have a direct connection from the gate to the drain or source? Do you? From gate, drain or source, do you have a direct connection in between? No. So they are AC coupled, not DC coupled. Do you understand what I'm saying? They are not DC coupled. There's no direct connection, wire connection, but they are AC coupled. Why? Because there's a capacitor here. So AC signal will pass, DC will be blocked. So they are AC coupled, not DC coupled. So you look at here, I don't want to directly make the connection because they are not DC coupled, but they are AC coupled and short to ground, because if I model it this way, VDD will be AC ground. Okay, these are the caps being modeled. So what is C in here? From the input, there's a little person standing here, right? Definitely a girl. I'm not intending to draw that, but when this guy's looking inside from the gate, what is the capacitance this guy is seeing here as the input capacitance? Yeah. Why? Because this one used to be only half CUX. Because the Miller effect, this one becomes CUX, right? And this is a half CUX. There's going to be one CUX added to half CUX, which becomes 3 halves of CUX, right? So what is this? Why do I model it that way? So it's actually, so this cap is actually, you split this cap in two caps, right? Split this one in 2 caps, and each of them is 1 CUX. So this is another CUX you have. So what is this though? Yeah, that's a C load. I didn't draw it here, but a lot of times the transistor, if you just draw a transistor in the circuit, doesn't connect to anything, it doesn't make sense. So whatever afterwards will be the C load. Okay, this is how we draw the model. I think after the break, we'll learn how to draw the PMOS model and analyze some of the digital circuits by using the models, and everything start making sense, including the ring oscillators that we did. Why the ring oscillators frequency is calculated that way? It's all because of the digital models. You know, all the CUX and C load in there. Okay, I think that's it. I want to cover today. If I don't have enough time to cover more, you guys have a nice break. I'll change the deadline of the second task after the class, and you can refresh the web page and find out the new dates over there. Okay.